Welcome to the Deep Dive, where we take your sources and extract the knowledge you need. Today, we're plunging into a really fundamental concept from computer science, how we systematically explore a binary tree.
That's right. We'll be using insights from Section 7.2, Binary Tree Traversal, in the text Hello, Algo. And our goal isn't just listing methods. We want to really get how they work, why they're different, and what resources they actually use.
Exactly. Think of a binary tree, maybe like an org chart or a decision tree, even like folders on your computer. Navigating every single item in that structure in a really defined order, that's traversal. And understanding how to do it is, well, it's crucial for working with this kind of data.
Yeah, absolutely. So our mission here is to make these common traversal methods just crystal clear. We'll look at the logic, the tools you usually use to implement them, the cost. So these ideas really stick with you, hopefully for the long haul.
Okay, let's unpack this then. What's the main challenge, moving through a binary tree compared to something simpler, like a list?
Well, a list is just linear, right? You follow the chain start to finish.
Mm.
Easy. But a tree, as the source points out, it's nonlinear. It branches out.
Yeah.
From any node, you might have a left child or right child, maybe both, maybe neither. So you can't just follow one path. You need a strategy, a systematic way to hit every node exactly once without getting lost or, repeating yourself.
Okay, so you need a plan, like a map, to explore all the branches without missing anything.
Precisely. And Hello Algo lays out four main ways to do this: level order, pre-order, in-order, and post-order. And these four actually fall into two sort of main strategic categories.
Okay, two categories. What's the first one we should dive into?
Let's start with level order traversal. This one explores the tree layer by layer. You start at the root, the very top, and then you move downwards level by level.
Layer by layer. Okay, so you visit everything on level 1, then everything on level 2, and so on.
Exactly. And within each level, the standard way is to go left to right. The source has this brilliant description, calls it a circumferentially outward expanding process.
Huh. Circumferentially outward expanding. I like that. It gives you a real picture, like ripples spreading out from the center.
Yeah, it's a great visual. It's basically a type of breadth-first search, or BFS.
BFS. Okay, so how do you actually do that? How do you keep track of the nodes when you're going level by level?
Well, the typical tool for implementing BFS on a tree, and therefore level order, is a queue.
A queue, like waiting in line. First one in is the first one out.
Exactly that. FIFO, first in, first out, and it's perfect for this. Here's how it works, roughly. You start by putting the root node into the queue. Then you loop, as long as the queue isn't empty. In each step, you take the node from the front of the queue, that's the one you visit or process. Then you add its children, usually left child first, then right child, if they exist, to the back of the queue.
Ah, I see. So you take one off the front, process it, and put its kids at the back.
Right. And because you're always adding the next level's nodes to the back, you'll finish processing all the nodes from the current level before you ever get to those ones you just added. It naturally enforces that layer by layer left to right order.
Okay, that makes a lot of sense. You process level 1, adding level 2 nodes, then you process level 2, adding level 3 nodes. Neat. What about the cost? The source mentioned complexity.
Yeah, for level order, the time complexity is ON. That's big O of N, where N is the number of nodes. It's pretty straightforward because you have to visit each node exactly one time.
Okay, O and time. Makes sense. What about space? How much memory does it need?
The space complexity is also ON. Now, this happens in the worst case. Think about a really wide, bushy tree, like a full binary tree. The bottom level can have, like, roughly half of all the nodes. At some point, your queue might have to hold all the nodes of the widest level simultaneously. Since that widest level can contain a number of nodes proportional to n, the space needed for the queue is ON.
Got it. ON time, ON space for level order. Uses a queue, goes layer by layer. Okay, so what's the other main category of traversal?
That would be depth-first traversal, or DFS. The other three methods we mentioned, pre-order, in-order, and post-order, they all fall under the DFS umbrella.
Depth first.
Yeah.
Okay, so the name implies instead of going wide across layers, you go deep first.
Exactly. You follow one path, one branch, as deep as it goes before you backtrack and try another path. The Hello Algo text uses another really helpful analogy here. It compares it to walking around the entire binary tree. Imagine tracing the perimeter. As you walk this path, you encounter each node at different moments relative to when you explore its children.
Walking around the perimeter. That gives a very different feel than the spreading wave of level order. Proceed to the end first, then backtrack.
So how is this usually implemented? If level order uses a queue, what does DFS use?
The most common way to implement DFS on a tree is using recursion.
Recursion,
Yeah.
where a function calls itself, right? Exactly. It mirrors the idea of going down a branch quite naturally. The source breaks down the recursive flow into two key actions, recursion and return. Recursion is when you make that function call to go deeper into a child's subtree. You're moving down the path. Return is when a function call finishes. That signals that everything within that subtree has been handled according to the rules, and you're essentially backtracking up the tree.
Right, so the function calls build up as you go deeper.
And the system uses the call stack to keep track of where to return to.
Okay, so you dive deep with these recursive calls, and when one finishes, you pop back up. And you said there are three types of DFS, pre-order, in-order, post-order. How do those differ? Is it about when you process the node?
Precisely. That's the key difference. It's all about the timing of the visit, when you actually process the current node's value relative to the recursive calls for its left and right children. So, for pre-order traversal, you visit the root node first. Then you recursively traverse the left subtree. Then you recursively traverse the right subtree. So the order is root left, let tree.
Root first. Okay, pre means before. Got it.
Then, for in-order traversal, you recursively traverse the left subtree first. Then you visit the current root node. Finally, you recursively traverse the right subtree. Order, left, root right.
Okay, root in the middle. In means between. Makes sense.
And lastly, post-order traversal. You recursively traverse the left subtree first, then you recursively traverse the right subtree. And finally, you visit the current root node.
Order. Left, right, root.
Root last. Post means after. Okay, that naming convention actually makes it much easier to remember. Pre, in, post just depends on where the root visit happens. The source also mentioned, I think, that you can do DFS without recursion.
It does, yeah. It notes that DFS can also be done iteratively. Typically, you'd use a stack data structure for that. An iterative approach basically mimics the recursion's call stack explicitly using a stack you manage yourself. It's not detailed deeply here, but it's good to know there's an alternative.
Always good to know there's more than one way. So what about complexity for these DFS methods? Time and space. Still ON. Yes. The time complexity for all three pre-order, in-order, post-order is ON. Just like level order, you have to touch every node once.
And space. Is it also ON?
It is also ON in the worst case, but the reason is different from level order. With recursion, the space is primarily used by the call stack. Now imagine a really skewed tree, one that looks almost like a linked list, where each node only has, say, a right child. In that scenario, the recursion could go n levels deep before it starts returning. The system needs to store information for each of those active calls on the stack, so that requires ON space. And if you use the iterative stack approach, that stack could also grow to size ON in that same worst-case skewed tree scenario.
Ah, okay. So level order space depends on the width of the tree, while DFS space depends on the depth or height of the tree, potentially reaching ON if it's very deep and skinny.
That's a great way to put it, width versus depth.
Okay, so summarizing. We have level order, BFS, using a queue, going layer by layer, and then the DFS family, pre-order, in-order, post-order, typically using recursion, going deep before backtracking, both generally ON time ON worst-case space, but the
These guys isn't just, theoretical. They have real uses. For instance, the text mentions in-order traversal. If you have a special kind of tree called a binary search tree, or BST.
where things are already ordered, like left child is smaller, right child is bigger.
Precisely that. If you do an in-order traversal on a BST, you actually visit the nodes in ascending sorted order.
Whoa, really? Just by visiting left root right on a BST gives you a sorted sequence. That's pretty cool.
It is, right? It falls out naturally from the structure and the traversal order. Very useful property.
And what about post-order? You mentioned that might be useful for deleting things.
Yes, post-order, left-right root, is often used for deleting nodes or even entire subtrees. Because you process the children before you process the parent, the root of the subtree you're considering, you can safely delete the children first. You work your way up from the leaves, ensuring you don't delete a parent node while you still need to access its children.
Okay, that makes sense for cleanup. Visit the dependents before the thing they depend on.
Yeah.
So, in order for sorting on a BST, post-order for safe deletion, these different orders clearly have practical value. It's not just arbitrary.
Not at all. The sequence matters, and choosing the right traversal depends heavily on what problem you're trying to solve with the tree. And thinking about these different systematic paths, the broad wave of level order, the deep dive of DFS, it kind of leads to a bigger question, doesn't it? Beyond just visiting, How might knowing the specific sequence generated by these traversals, how could that sequence itself be useful? Could you, say, reconstruct a tree if you only knew its pre-order and in-order sequences? Or could these ordered patterns help solve problems that don't even look like trees initially? When does the order itself become the key piece of information?
That's definitely something interesting to think about. When the journey, not just the destination nodes, holds the answer. Hopefully, this deep dive has given you a clearer map for navigating these branching structures yourselves. Thanks for joining us.